Hello, this is Dr. Armand again, bringing you another exciting lecture on general chemistry. Today we'll be focusing on electrochemistry, namely how to find delta G and K when given cell potential and showing the relationship between the two, calculating E of cell at non-equilibrium conditions, such as using the Nernst equation, and finishing off with calculations involving electrolytic cells. This will be the last lecture in this series of lectures over the second semester of general chemistry topics. So today is like the season finale of my lectures. So sit back and relax and enjoy the show. And so this is part 3 of electrochemistry lectures. We'll be talking about the relationship between E of cell, equilibrium constant, and delta G, how to do calculations for those different quantities. Looking at the E of cell non-equilibrium conditions, aka the Nernst equation, and then finally finishing off with some calculations involving electrolytic cells. So we can show that there is a relationship between delta G. Delta G is proportional to the E of cell. Now it's proportional to the negative E of cell because if we remember correctly in earlier chapters, delta G is negative, means it's spontaneous. However, when E of cell is positive, it's spontaneous. So we can use this expression here where delta G equals negative NF E of cell. Now F is a constant, the Faraday constant, which is a joule per volt times mole of electrons. N is the moles of electrons in a balanced redox reaction. And by knowing that, you can determine the delta G if given the cell potential, or determine the cell potential given delta G. So for equilibrium, we learned that delta G is related to the equilibrium constant by this negative RT ln of K. We can substitute negative NF E of cell for delta G. We get the relationship between E of cell and ln of K. Now we can simplify this. So we get E of cell as RT over NF. Again, R is the constant 8.314. T is the temperature. Now, if it's at 298 Kelvin, we can simplify it to this form here. So the bottom form, again, is when the temperature is addressed at 298 Kelvin. We can use this reduced form here. Now, if you want to see the conversion between this and this, from here to here, you can look in your book and they explain how they got from ln of K to log of K. So this is the triangle of life with E of cell, K, and delta G. So when delta G is negative, we learned from last chapter that K is greater than 1. And in this chapter, we learned that E of cell is greater than 0. So this means that it is spontaneous. When delta G is positive, we know that K is less than 1 and E of cell is less than 0, which means it's non-spontaneous. And this shows you the equations needed to calculate between the different variables. So if you have E of cell, you can calculate K and delta G. If you have K, you can calculate E of cell and delta G. And of course, if you have delta G, you can calculate E of cell and K. So here we have this reaction. It's given us the E of cell, this reaction, 0.25 volts. We know that it's spontaneous because it's a positive E of cell. It wants us to calculate K and delta G at 298 Kelvin. So this is the equation we're going to use to calculate K. So we need to know N, which is the moles of electrons. And you can find it a variety of ways, but what we want to look at is we got to determine how many electrons have been transferred. So in this balanced equation, you see that copper has 3 and copper 2 plus has 3. So each copper gives up 2 electrons. So if we have 3 coppers, they give up each 2 electrons. That means we're going to have 6 electrons that were given up or transferred. That's one way to find N. So if we rearrange this to solve for log of K, of course we need N. And we look at the half reactions. So copper is oxidized, permanganate is reduced. Again, what was it? Permanganate is a very strong oxidizing agent. And so we can balance the electrons by doing this. So you see that 6 electrons are being transferred. We plug that into the equation. We solve for K. So K is 2.2 times 10 to the 25th. This doesn't surprise us because it's a spontaneous reaction. K should be large. Now, if we wanted to write the shorthand for this reaction, it could be something like this: copper plus 2, permanganate, MnO2, and then we need a inactive electrode such as platinum. Now to calculate delta G, remember that delta G equals negative NF E of cell. So F is Faraday constant. And N is the moles of electrons transferred. So that's 6. Now we can plug it in and solve for delta G. And we get negative 14 or 100 or 1.45 e to the 5th, 145,000 joules. Convert this to kilojoules, get 145 kilojoules. This makes sense because E of cell is positive, delta G should be negative. So that's the delta G of this reaction. Now, how does concentration affect cell potential? So in the last chapter, or in the previous chapters, we learned about calculating delta G at non-equilibrium conditions. So what we're going to do is we're going to take that equation, and for everywhere we see delta G, we're going to substitute in negative NF E of cell. And so that helps us derive what is referred to as the Nernst equation. So ln of Q, remember Q is equal to the concentration of products divided by the concentration of reactants. N is number of moles transferred, R is 8.314, temperature needs to be in Kelvin, and F is the Faraday constant. So if you're at 298 Kelvin, you can use a reduced form of the Nernst equation using log of Q. Again, this is only at 298 Kelvin. So here we have an example of when we have to use the Nernst equation. And again, it's going to give you the Nernst equation, or you're going to use the Nernst equation when you're given cell potentials and concentrations. So we have this voltaic cell, which consists of a chromium and 10 half cells with the concentrations of their respective ions. It wants to calculate the E of cell at 298.15. And this is a voltaic cell, so you have to arrange these half cells such that we get a positive E of cell. And we learn these are the reduction potentials. So the one with the more negative reduction potential is the one that wants to be oxidized. So our anode is going to be chromium. because it has the more negative reduction potential, so it's going to be the one that's going to get oxidized. So we're going to use this equation. We need to determine the moles of electrons and Q, and also the standard cell potential. So oxidation is chromium. That's because it has the more negative reduction potential. Tin is being reduced because it has the more positive reduction potential. Q is the concentration of chromium 2 plus over tin 2 plus. And again, that's because chromium 2 plus is the product, tin 2 plus is the reactant. And again, the way I know it's this because we're talking about a voltaic cell, which means it has to have a positive E of cell. And so therefore, chromium has the more negative reduction potential, so it's going to be oxidized, tin is going to be reduced. And so Q is equal to the concentration of chromium divided by tin. And it's in a balanced equation, it's only 1 to 1. Plug in the concentrations, Q is 8. So this tells us we have a lot of product, very little reactant. Now before we move further, if I was to write this shorthand configuration, it would be chromium plus 2, tin plus 2, tin. So now we plug Q in, and we know N is 2. We can determine the E of cell. Now the E standard of cell is the E of oxidation plus E of reduction. The E of oxidation of chromium is 0.91, so we get a positive cell voltage. We plug all that in. We get E of cell has decreased a little bit, and that's because we have a lot of product, little reactants. So if you increase the concentration of reactants, you're going to increase your E of cell. If you increase the concentration of products, you're going to decrease your E of cell. So we're going to spend a little time on electrolytic cells, or the stoichiometry of electrolysis. And in electrolysis, what you have to do is, if you want, you have to apply energy, aka electrical energy, to make the reaction occur. And so usually you apply it in amps over a given unit of time. And the reason we apply amps over a given unit of time is we can calculate something called charge. So amps is a coulomb per second. And so if we know the current, we can find the charge. And once we find the charge, we can use that to find the moles of electrons that was transferred. And then we can find the moles of substance and then the mass of substance. So in electrolysis or electrolytic cells, you're either going to go this way if you're given current and time, for example, or you're going to go this way if you're given mass and want to find current. You're going to do one of these directions regardless. And so you're going to need a balanced half reaction to find the moles of electrons you need for each mole of product. You're going to use the Faraday constant to convert from charge to moles of electrons, or moles of electrons to charge. You're going to need to know the molar mass to find the moles of product, to get the moles of electrons and then the charge. Or you're going to be given, you're going to use the current to find time, to get the charge, to get the moles of electrons and the moles of substance. So you're going to go either one of two directions on this. So let's look at a few examples of electrolytic cells. So here we apply a current of 4.75 amps. How many minutes does it take to plate a sculpture with 1.5 grams of copper from a copper sulfate solution? So again, current is charge over time, and if we're looking for time, time is charge over current. So we need to know the A charge that was applied and B the current to determine time. And so the current is given to us, it's 4.75 amps. So we need to find the charge. How do we find the charge? Well, charge is equal to the moles of electrons times the Faraday constant. We can find the moles of electrons from the moles of substance using the half reaction. And then once we know the moles of substance, we can find the mass of substance. So if we know the mass of substance, so if we know this, the mass of substance, I know it's messy, then we can find the moles of substance, then we can find the moles of electrons, and then we can find the charge. And we know the mass of substance is given to us 1.5 grams. That's a little messy. Let me erase it. So we can find the moles of copper. Mass divided by molar mass gives us the moles. The reduction half reaction, for every 2 moles of electrons, we produce 1 mole of copper. That's a 2-to-1 ratio. So to find the moles of electrons, we simply multiply the moles of copper by 2, we get the moles of electrons. Now we multiply by Faraday's constant to get the charge. And then charge divided by current gives us time. So it takes 16 minutes at a current of 4.75 amps to produce or to plate a sculpture with 1.5 grams of copper. Here we want to know an element forms of the fluoride MF3. Now M is just a generic unknown metal. M could be anything. Electrolysis of the molten fluoride by a current of 3.86 amps for 16.2 minutes deposits 1.25 grams of metal. Calculate the molar mass of the element and determine its identity. So M we don't know. So we got to determine its identity and calculate molar mass. So what's molar mass? Mass of metal over moles of metal. Do we know the mass of metal? Well, yes, we do. It's 1.25 grams. Do we know the moles of metal? No, we don't. So we need to find the moles of metal. How do we find the moles of metal? Well, the moles of electrons can lead us to the moles of the substance. How do we find the moles of electrons? Well, we know that 1 mole of substance gives us 3 moles of electrons. So that's our relationship between moles of metal and moles of electrons. And why is it 3 is because our general formula is MF3. And this means that our metal has a 3+ cation. So the charge equals moles of electrons times Faraday. So if we know the charge, we can divide it by Faraday's constant to get the moles of electrons. And we know that current is equal to charge over time. So if we know the current and time, we can find the charge. Charge equals current times time. We have the current, we have the time, we can find the charge, then we can find the moles of electrons, then we can find the moles of the metal. Now time has to be in seconds when finding charge. So I converted 16.2 minutes into seconds, multiply that by the current, we get a charge of 3,752 coulombs. We divide it by Faraday's constant, we get the moles of electrons. 3 moles of electrons equals 1 mole of metal. So we get the moles of metal. Now we can get the molar mass of metal. And you see which element on the periodic table has a molar mass similar to this, and you look it up, it's molybdenum. So our unknown element, metal, in this case, is molybdenum. And so that's how you use electrolysis to determine the identity of your unknown metal. Now that concludes today's lecture over cell potential and Gibbs free energy with equilibrium constant, the Nernst equation, and electrolytic cells. And that also concludes the last lecture in this series for this second semester of general chemistry. So this is the season finale. So on that note, I hope you enjoyed the lecture series. I know it's not the same as being in class, but maybe it was you learned something from it. And if you did like the series or you liked this lecture, make sure to hit the like button. Or if you did learn something new, be sure to hit the like button. On that note, good luck, and Dr. Armand signing off.